what the government says. So the team behind this effort, so it was not creating a vacuum, of course. So I led this submission, but there were basically these 12 people involved in it, and so this is a joint collaboration between NERSC, so Lawrence Berkeley Lab, the NERSC division, NVIDIA, Oak Ridge, and UC Berkeley. So I want to thank everybody here for their contributions. By the way, this is Czech business. Right? So we're interested in extreme weather events. Why? Because they have a major, or like a big socio-economic impact, right? So when you think about Katrina in 2005, or Harvey in 2017, flooding, New Orleans, or Houston, respectively, especially when you look at the year 2017, there was $200 billion worth of damage incurred by extreme weather phenomena, aggregate. So that's quite bad. But even when you look at smaller scale events, for example, the so-called atmospheric rivers, so these are like long, basically like long currents, atmospheric currents, which can transport lots of water over long distances. They can also cause a lot of like rain, precipitation, and flooding. Like this is Berkeley, so it's hard to see, but it's basically Ashby Avenue flooded by an atmospheric river. So even these small events can cause some disruption. And more importantly, they also, since they're like responsible for 50% of the rainfall here in California, for example, they're also correlated with like how many forest fires we get, right? So like last year, like end of last year, we had this campfire in Santa Rosa with like a lot of people lost their homes, people dead, a lot of forests got burned, and we had a hard time breathing here in the Bay Area for like 2 weeks or so. So the cost estimate for one of these events was 10 billion for large event. So that can be quite costly. And you want to know, as an insurance company or as a government or state officials who need to plan like disaster mitigation strategies, you need to know what you have to gear up for. So in order to do that, we should maybe look first what a typical approach to climate analytics is. So you have these simulations. So these come out of some like model simulations, some traditional HPC simulations. So this is basically an image version of the data you get. You get basically fields for wind speed, temperature, pressure, gradients, humidity, things like that. And then you can create an image out of this. And what you see is a very high fidelity animation. And it's basically 40 million data points for a 3-hour time interval in simulation time. So and then you have like hundreds of years worth of data, right? Because you want to project the climate like in the future. So what you then do, like what people do, is they use these input images and compute like summary statistics on it. So for example, when you look at the IPCC report, these are like mean temperature rise over the globe, like over a couple of years. So they reduce this 40 million observables for a 3-hour like simulated interval to like 1, 2, 3 observables per year to make this plot. So this is a nice data reduction, but it's maybe not the thing you want to do. It's a bit too much. So you want to understand, or we want to answer, will there be more hurricanes, right? So that is number one. And if there are, will they be also more intense, right? So if they get less intense, we might not care that much, but we want to know both quantities here. And also, will they make landfall more often? If they stay over the sea, it doesn't matter that much potentially. Maybe they impact like sea traffic, but for like the most devastating impact comes when it hits the shoreline or like oil rigs or something. And also atmospheric rivers, will they carry more water? So do we have to like gear up for more rain? Maybe fewer forest fires, or maybe more if they change their direction, right? So if they don't hit the Bay Area that much anymore, we might get more forest fires. So that is very important to understand, and for that we need a high fidelity simulation. Analytics framework for the high fidelity simulations we already have. So we have these images, or like these video sequences if you want, and the easiest thing you can think about is like first just detect these objects, and then once we detect them we can do all sorts of things. We can correlate them with the underlying like region they pass over, like we can do a damage assessment. Depending on the resolution, we can do a damage assessment of like the underlying like cities or like whatever shorelines. When you correlate them with wind speeds, the humidity, the precipitation, all these kind of observables. So for this you need a flexible and scalable algorithm. So one thing is that climate change will change the underlying dynamics of the system. which means that if you have a handcrafted algorithm, which does this for you, and these algorithms exist, they are not as great, I will talk about that later, then that means that climate change can invalidate these algorithms. Because like the underlying assumptions on the system change, right? And your algorithm is not necessarily adaptable. So we want to have something which basically can adapt to anything. And also at the exascale era of supercomputing, which means in double precision having like an exaflop per second, or like compute capability of an exaflop per second, people are talking about climate models with 1 square kilometer spatial resolution, and you can do a lot of nice things with this, right? But if your data analytics lags behind, then it doesn't help you, right? It's really pointless to generate these ensembles. So this is what we want to do. We want to basically develop this framework to do a better data analytics. So let's start simple. So interpret this as an image segmentation problem, where you have 3 classes, which is like background, so nothing is going on, or nothing of interest. So there's a lot going on in the background, but nothing of interest. Tropical cyclones, which are hurricanes, or atmospheric rivers. So the good news is that these rare events are still rare in the future. So like about 95% of the pixels are still background. But that also means that it's a hard classification problem, right? Because you have a high class imbalance. You have like a lot of background, some atmospheric river pixels, and very, very few hurricanes. There's also high variance in the object itself. So when you think about street scene segmentation, right? It's a similar problem, it's a segmentation problem, and then you have like pedestrians, you have cars passing by. What you will see is that you will see, for example, cars from different angles, but they don't change the shape. They're still a car. Whereas these events, they can, for example, atmospheric rivers can bend around, they can grow, they can shrink, they can dissolve, these kind of things. And the background itself is not static or slowly moving. It's a lot of like things going on in the background as well. The input channels we have, or like the observables we have here, are of different types. It's not like the typical RGB image. What we feed to the network later will be input channels like wind speeds, temperatures at different altitudes, physical observables. And so deep learning has proven successful for this image segmentation task. This is what we used here. So what are the challenges for this? So for the best working deep learning approaches are supervised, so you need to provide a pair of data and label, right? So the problem is that you have a lot of these data sets, a lot of these data from these big data sets, and you need to get the labels. The issue is that so far they are not really human annotated data. A lot of human annotated data you can train a model on. So what we did, we used these old-fashioned heuristic-based approaches to generate labels. So we set up something which is like an Amazon Mechanical Turk for climate domain scientists, where like people from climate science can go and label these things manually online, and then we let a different number of people label the same set of images, so that we get some kind of like consensus on that. But for this approach here, for the project at that point in time, we just generate this label automatically, and I will talk about the drawbacks and the shortcomings of that. So we want to define a network architecture, right? And there you want to have a balance between compute performance and model accuracy. So the issue is that, of course, you want to have a deep enough model that you get a good accuracy. But on the other hand, you don't want to train very long, right? So in order to iterate over the models, we wanted to have a high productivity framework. So you can use Caffe, for example, which is very scalable and was already very performant. But we want to have something which is easier to use and easier to modify. And this is why we use TensorFlow for that. And the interesting part here is when you think about performance optimization, deep learning is a bit special. So when you, for example, look at a high-performance computing simulation, usually it consists of like a selection of kernels, and then you just go kernel by kernel and optimize it, and then look a bit at the communication, and you're done. Whereas here, when you start out with TensorFlow, a lot of the kernels are already highly optimized, and here the challenge is just that your whole network needs to be optimized. That means starting from the data, loading the data from this, feeding it to the GPU, processing in a forward step, and in a backward pass, when you compute the gradients, and in data parallel training, you need to reduce the gradients over all the nodes, So this needs to be done in a very optimal fashion, that your GPUs are basically pretty busy and not idle, and waiting for data or waiting for reductions. And you need hyperparameter tuning in order to converge your network, right? So once you have a network, you might still want to use some kind of like algorithmic or manual hyperparameter tuning, like the learning rate, the layer sizes, kernel sizes, in order to get the best accuracy you can think of, or you need. So at extreme scale, you have some more challenges. This is especially the data set. So we had only 20 terabyte here. We have like a 400 terabyte lying around. For this study, we used 20 of that. Because this was also feasible to label in a short amount of time with these old algorithms. So we need to feed this data set to keep the GPUs busy. So that's one tricky part. So if you think about like everybody reading from a global file system, that is bad. So I will show a result on that. So also you need to do this synchronous reduction, this gradient reduction, which is about 50 megabytes or more at every time step, and the time steps are very short. Across, for example, 27,000 GPUs if you want to run on the whole system, and that is very expensive. You need to make sure that you still converge at scale. So when you do data parallel training, basically your global batch size, you basically duplicate the batches, or you do not, so your local batch size per node for the training stays the same. That means by adding more nodes, your global batch size grows. And that can impact conversion accuracy negatively. So that you need to take into account and need to use like more sophisticated algorithms to mitigate this issue. You cannot, it's not completely solve this problem, but you can work around this a bit. And of course, again, you might need some hyperparameter tuning while you scale out. For example, normally you need to adjust the learning rate. And also that is a bit of a tricky, messy business, more or less try and error. There are a couple of, a lot of papers about this, but there's one-size-fits-all kind of solution. It doesn't exist, unfortunately. So, labels. I talked about that we have these old algorithms, so what do? So we have the output of the climate simulation. It predicts, for example, water vapor, wind speeds, humidity, these kind of things. And then you do manual feature engineering. So you compute observables like, so one important one is the so-called integrated water vapor transport. Don't try to remember this. It's just like, it's basically what computer vision did like 10 years, 20 years ago, when everybody was designing their own features, which basically helped you, for example, to detect a tree in an image, right? So this is this was for a long time the state of the art in climate science as well. So once you have this field here, what you do is you can binarize it by applying a 95 percentile threshold, and you end up with these patches, and then you apply some domain knowledge, say, okay, so these could be atmospheric rivers, but they do not occur like around the equator and at the poles, so just cut them out and you're done. So this is our candidates for labels. So there are a lot of things which can go wrong here, like is this really the good feature? Is this threshold good enough? So if you make it more aggressive, like if you raise it, you get smaller but then sharper labels. And if you make it lower, then you get like more wobbly labels, right? But that's also clear when you look at a hurricane, it's really hard to see where it starts and ends, for example, right? Or like at these objects. So yeah, hurricanes are similarly. So here you have to be a bit careful. You cannot just apply this same method to the whole globe. You first need to find like regions of high vorticity or like a certain kind of like pressure gradient, right? And then you basically extract a patch, like a center point, and from that you can extract like a bounding box of the typical size of a hurricane, and then you can apply a certain flood flow algorithm here, which is basically based on water vapor and precipitation. So that's the thing. And here you can see like the label is a bit fuzzy, right? You can depending on whom you ask, you might say, okay, oh, this is good, or like, oh no, this is much too aggressive. You can be more conservative and make it bigger. So these are the drawbacks of, or the shortcomings of these algorithms. It's also that they don't work well on all regions of the globe. So in some regions of the globe, they find more hurricanes than on others, although there are like the same number of hurricanes approximately. So there's regional dependence, there's a lot of parameter dependence here, which make these algorithms a bit bad. But nevertheless, we use these to label the data for networks, and actually a network was able to learn something more sensible from that data, which is quite interesting. Good. So what kind of software stack did we use? We used TensorFlow and Horovod. So TensorFlow, I don't know if I need to explain it, maybe I should. So it's a high productivity deep learning framework. It uses It's basically Python. It's like a domain-specific language. You express your network in Python, but under the hood, it compiles into a graph of C++, into a graph which makes callbacks into C++ functions, and it also makes use of like optimized library like QDNN, which is the library by NVIDIA, which contains a lot of deep learning primitives for GPUs. So for Intel, it would make calls into NKLDNN, for example. It is data flow style, so it cares about like, so every operation is a node in the graph, and then you have like data edges coming in, and then as soon as the resources are available and the dependencies are met, it will execute a certain block of data. The cool thing about it is it provides a lot of features for building an efficient I/O pipeline, and that is what a lot of frameworks lack at right now. And it's very, very important when you have like big data and you want to really feed it efficiently to GPUs. So TensorFlow is one of the better frameworks here. And the good thing is you can compile it mostly with some limitations with most other Python modules for some flexibility. So Horobot is developed by Uber, and it's I call it distributed training enabler, because TensorFlow can do data parallel training, but they have like a very, very horrible backend. It's called gRPC. It's based on TCP/IP and has a lot of like overhead, and setting it up on a supercomputer is a pain in the neck. Whereas Horobot just technically provides callback functions, so convenience methods which make calls into MPI, right? And MPI, message passing interface for supercomputers, is pretty well optimized, right? Because like in the HPC, so HPC, a lot of people use MPI. So in every supercomputer you buy, MPI is already very well optimized for the architecture. So that's why Horobot is pretty nice. And also, when you have for example, a TensorFlow program like the Python notebook, Python script with your TensorFlow code, you have to just change 4 lines of code to make it like distributed, and that's it in theory. Okay. The cool thing is it operates asynchronously with the TensorFlow graph execution, which means that you can overlap communication and computation nicely. So you don't have to work that hard. You have to work a bit, but not that hard to get a nice overlap here. So the systems we ran on were, one was Pistain. This was like a reference system we used to see like because technically for this study we want to see like that we like get good performance on more than one available system. So this is a Cray XC50 at CSCS in Switzerland. I don't know if it's still top 5, I don't know anymore, but it's 5,000 nodes with Intel Xeon E5 and 1 NVIDIA P100 GPU, so the last generation of the NVIDIA professional Tesla GPUs. And it's 54.4 petaflops peak performance in single precision. So I don't quote double precision here because as a deep learning guy, I don't care about double precision at all. Summit, of course, is the IBM and like Oak Ridge flagship system. So first on the top 500. It consists of 4,600 nodes so every node has like 2 Power 9s and 6 NVIDIA V100 GPUs. And the GPUs are connected using NVLink, 300 gigabytes per second, and also have a high bandwidth connection to the CPU. A very cool feature is this node local storage, the NVMe. So it's non-volatile memory, right? And it's 800 gigabyte. And we did some benchmarks on the bandwidth of this thing, and it's almost DRAM bandwidth. So it's like a DRAM with 800 gigabytes, which is really good. High-speed network, but the most amazing part here is that, in theory, if you can get along with FP16, this is an exascale system. So it can do 3.4 exaflops per second, so 10 to the 18 floating point operations per second as in FP16. Because people, so we have this exascale computing project for the next generation of machines, which should reach exascale performance in double precision, so FP64. This is what everybody is excited about, but you can have exascale right now if you have mixed precision code or FP16 ready code with the right mix of operations, of course. But then you have a lot of opportunities here. So, how do these segmentation models work? I don't want to go into detail here. They're like, we train 2. One is called Tiramisu, the other one Deep Lab version 3+. They are pretty similar. So like they have an encoder part, which it takes the image or like the input tensor, extracts features at different levels, like different resolutions, And then that is fed into a decoder, and the decoder basically uses the extracted features to make a prediction for each pixel. And to allow for multi-resolution, you basically feed in at different stages from the encoder, you feed in with the so-called skip connections, you feed the features back into the decoder so that it can make a better guess. Because some of these features extracted here get lost on the way, right? And you basically want to avoid that, and this is why you have the skip connections. So Tiramisu is like 35 layers. It's pretty deep already, but it's not like tremendous. With 7.8 million parameters, and the processing, so to process a single sample of data costs 4.2 teraflops, so forward-backward pass. DeepLab version 3 Plus, so this is a version, a modified one. So the original one has a decoder, just the bilinear interpolation. So replace this with the fully deconf decoder. So this is it can technically learn a better representation of the data, and also it can make pixel level predictions. The original DeepLab version 3 Plus had some limitations, and then they needed to apply some cleanup algorithm after the fact, right? So to basically get the pixel level resolution they want. So we said, okay, we don't want that, and we have a lot of computational power. So this is why so Google designed the other one with the limited computational power in mind. So we have a lot of that, so we don't care, we just do the real thing and make it like fully deconvolutional. So we cranked up the number of parameters to 44 million by that, and to process a single sample is now 14 teraflop, which is quite expensive. Okay, so let's talk about the whole pipeline. First we need to stage the data. So we have 20 terabytes, and the required bandwidth to feed 27,000 GPUs efficiently is 3.8 terabytes per second aggregate bandwidth. So if you look at GPFS or Lustre, it's like 40 gigabytes per second. You see what you get in ideal benchmark cases, but usually you get less. Burst buffer, like we have on Cori, like the Cray data warp, for example, is can get you like 2 terabytes per second if you're lucky. But I think the best bet here is you have NVMe or DRAM, which can get you an aggregate bandwidth of 26 terabytes, which is great. So what you do, you have the data set, shuffle it, and then you just stage it into the NVMe. This is what we did. So once it's there, you still need to feed it, right? So the files are Android HDF5, which is a very popular file format. It's a self-descriptive file format, like the hierarchical data format in science. So scientists like it. I like it too, but it has some shortcomings because it serializes accesses under the hood. So when you try to open even if it's only for reading, if you try to open with different threads, different HDF5 files, you make a call to the same HDF5 library, there will be a lock which will basically serialize the access. It's a bit annoying. So you can circumvent this by using Python multiprocessing and just fork four processes, for example, to do that in parallel. So then you have like 4 different library instances which will then not serialize anything. So we have on the CPU, what we do, we have this list of files, just the strings, right? Not the content, just the strings. Shuffle that, and then you do a 4-way parallel read, batch it up, and feed it to the GPU. So that is like all on the CPU here, together with some minor pre-processing, like data normalization, and then it will basically send off to the GPU, which will do the training. So this can be easy, nicely done TensorFlow, by the way. Okay, so for the single node performance, let's have a look at that. We use the QDA profiler NVProf for that. It basically tells you the execution time for different kernels, also the memory consumptions for the kernels. And I want to point out first that they have a lot of kernels. So there's really like no point in trying to optimize a single kernel here because these are all like different kernels, or maybe the same kernels but with different parameter set, right? It doesn't make sense to optimize just one instance of it because yeah, I mean there are too many of them. Another thing I want to point out is what is good here is that the time spent in actual flops is high. It's like 18% and 36% in forward-backward paths. But also what is not so great is these copy and transposes. So TensorFlow inserts a lot of like data copies and transposes in order to map the layers together to get the data layout optimal. And we reduced this by quite a lot already, so this is already an optimized version of the network, but it's still inefficient. And we talked to the TensorFlow team about that, and they're looking into this. Because, for example, when you concatenate 2 tensors, even if it's on the slowest index, where you can just basically concatenate the pointers, it will create a new buffer and copy the data in. So you blow up your memory consumption artificially by this. So this model, the model we have, could have easily fit into maybe GPU memory twice, but due to this problem here, we had like we basically blew away the memory, and we could have fit the model once plus like just one batch. So the idle time is 1.7% of the time, which is very good, but that also tells us if we optimize anything here, the idle time will probably go up, because what this tells us is that it still waits for data. So the data pipeline is already very good, but it's not like 100% optimal yet. So however, that's good enough for us. Okay, so Horobot. Coming to that. So since everything is asynchronous here, so Horobot takes care of the reductions of the gradients in each step. So every weight in every layer has a gradient, right? Which needs to be reduced. The problem is that since this is asynchronous and the network has branching points, you don't know actually what gradients are ready at a given point in time. So for that, you need to figure out actually which gradients to reduce. So what Horobot does, it takes the list of the gradients which are ready, so not just like string indicators, like, okay, tensor 1, 2, 5, 8, 13 is over here, the second node is 1, 3, 5, 7, 13, and so on. And then it will send all these lists to node 0, or node 1, it will do list intersection and broadcast it back. And you can, and then, okay, so say, okay, 5 and 13 are ready, just reduce these. What you can see here is it's not efficient. So when you scale this out, right, everything is piped through a single node. So you have this one-to-many, many-to-one communication is pretty bad. So there's we thought, come on, this is an HPC 101, like do your homework, man. So it just replaces by a tree, an array tree, and it's fine. So that works much better. So that was one optimization we did, and we have a variant of that. So Uber didn't like it; was too complicated for them. So we have a variant of that which is similarly good as a pull request open into the Horobot. So for the OREDUCE itself, you can just call MPI OREDUCE, but there's a catch. So Summit has this nice, or this, not nice, it's like this peculiarity that you have 3 GPUs, and you have 2 virtual interconnects per GPU, per group of 3 GPUs, per socket. So you can either call the OREDUCE and hope that everything will work out, but what you'll see is that 2 GPUs get full bandwidth and the other one has to wait for the others to complete. So what you can do instead is you split this up in 3 phases. So the first is you do an intranode OREDUCE using nickel, which goes through the NVLink connection. So there's no outside communication. And then you pick 2 GPUs and do the external off-node reduction. And once you have this, you still need to get the other 2 GPUs basically updated, and that you can do with a broadcast in nickel. So by that you circumvent this bottleneck over MPI. It's unfortunate that this has this topology, but this is very specific to the Summit system, so like other systems which are more balanced don't have that problem, but it was crucial here to get decent performance. Okay, and the cool thing is you can basically overlap some of these communications nicely. So this will happen automatically because nickel and MPI can work simultaneously. Okay, so last one was an algorithmic change. This is, I think in deep learning communities is quite, it's not common. People know about it, but not many people use it because they don't go to like tremendous scales. But what it actually means is the following. So when you have your weights, and you wanna update them, you compute the gradients, you reduce the gradients, and then you feed them back into the model. So you can do this, but then of course you have to wait for the gradient computation, then you OREDUCE, and then you can integrate it. So what you can instead do is, while, for example, on the GPU, you compute the fresh gradients for the current model, you just pop from a queue gradients from the last step and reduce those instead at the same time. So on the CPU, you have this buffer with like old gradients. You pop them, OREDUCE them, and feed them and update the model, while at the same time you compute the new gradients. There's of course a problem when you think about this as like, so this is an optimization problem. You compute technically the derivative with respect to an outdated point, right? Or basically, you use gradients which are older. You are on your optimization manifold, you are at different points, so you use the wrong gradients. That means that technically it can impact your convergence negatively. And I have a plot about that. But at least it allows you to overlap this much, much better. Okay, so let's talk about performance now. So these are images per second versus number of GPUs. This is on Disdained, because this is the only system where we tried that. Where we just read the data from local, so from DDR, or from global file system. What you can see here is that is the performance we got on 2,000 GPUs. That's not even a big scale, right? That you get a 10% penalty just by reading data from the global file system, because it's so inefficient. Because HPC file systems are optimized for writing big chunks of data, but they are not very good at reading small bits in an almost random fashion. So if you go out further, like to 4,000 GPUs, this curve will totally bend down and the performance is totally bad. It's worse than on 1,000 GPUs, for example. I don't want to plot it because it looks so depressing. Okay. So that tells you stage your data into like local memory, or like if you're a system integrator, build a system with lots of RAM and like NVP, for example. That helps. Okay, Tiramisu scaling. I don't want to talk a lot about this. So you see the Disdained results are here. So this is a much smaller and older machine. So it's like that's fine. This is images per second, number of GPUs. And this is the petaflops per second, so more like the HPC metric. The blue line is summit in single precision, and the red line is summit in half precision. And what you can see here, you see this big performance difference, because in half precision you can use the NVIDIA tensor cores, which can deliver, in theory, like 125 teraflops. I think if you just do a series of HGEMs, so of small matrix multiplications, what you will end up is like something like 100 or like 90 teraflops. But still, it's much more than just a factor of 2 improvement, what you usually have when you reduce the precision. So what you can still also see here is that when you use these tensor cores, your GPUs are so fast that you are very sensitive to communication. So in that case, you really want to use something like this asynchronous updates, which allow you to better hide communication behind computation. And that's actually what you see here when you go from the light red line to the solid red line. So for Deep Lab, this looks similar. We only ran this on Summit. I don't want to go into detail here, but what you can see is that we got on 27,000 GPUs, we got already almost to an exaflop. So this 1,000 petaflops per second is the exaflop mark, and we thought like, gosh, I mean, we want to get there, right? I mean, this looks ridiculous. So we tweaked the model a bit more. So especially the decoder part, we haven't taken care of. So we haven't looked at this that much at that point because we thought like it's fine. But we found like TensorFlow is doing a lot of like stupid things, like this additional transposition I was talking about. And by reorganizing basically the data order, we could get rid of them almost fully for the decoder. And we just used a couple of nodes more, and what we got was this 999 petaflops per second FP16 as sustained performance on 27,360 GPU, and as peak performance is 1.13 exaflops. Or call it exaops. If you don't like the notion of FP16 exaops, please. But it's definitely one of the biggest, I think the biggest deep learning calculation officially published. So, okay. Convergence. So these are just convergence curves. So this is for Tiramisu. The issue is like the machine was new, so we didn't have like a lot of time to do a very thorough convergence story on all the different cases, all the different networks with all the different concurrencies. So we started with the Tiramisu one on a medium-sized scale. And what you can see here is that going, for example, from 384 to 1,536 GPUs, you get about a 2.1 improvement in solution. It's not the best strong scale you can hope for, but it's good. So it's strong scale, right? It's basically you hope that by going to more nodes you improve your time to solution. That's actually what happens here. And that's the harder problem than the usually weak scale where you just increase your problem size. So the model lag. So this is the asynchronous updates. You can say, okay, so we have this outdated gradients we feed into our model. This is really good, and here you can see it is so. Look, just forget about the red curve here. Look at the dark blue and the light blue. So the light blue is the Deep Lab one without, so with the synchronous update plotted against the wall clock time in seconds. And it converges nice, so loss is nicely reduced, and then it nicely like converges, right? When you have this asynchronous update, at the beginning it's very unstable because it's like it does random stuff. Basically it does a random walk. But at some point it catches itself and then outperforms in wall clock time the fully synchronous version. Now you can of course combine this and say, okay, maybe I run my model in fully synchronous without lag for the first like 2,000 seconds and then switch to the asynchronous case. So that is the best solution you can do, but we haven't implemented that. Okay, so that's the results for the segmentation. So the segmentation results. On the left-hand side, you see the predicted patterns from the model. On the right-hand side, the ground truth. So I want to mention 3 things. First, we could get, if you wanted to 73% intersection over union. It's basically a metric how good these labels overlap with the ground truth. The issue is the labels are not great. So please, this is why you should take this with a grain of salt. It doesn't help you to really improve the performance like crazy here, because if you match something which is already bad, this is maybe not the best approach to do. The other thing what you see is there is some qualitative agreement, of course. But what you also can see is that we overpredict hurricanes here. So we looked into this, and actually showing this to domain scientists, they said that most of the objects the network detects, which are not in the label data set, are real. Or you would say a human could label them as real. The other thing is, you can see this, that on the right-hand side you see a lot of flickering. And this is because of the aggressive thresholding. So what this means is that you have this sequence of images, and then you would detect this algorithm detects a label, in the next frame it doesn't, and then it detects the atmospheric river again. Of course, in a 9-hour time interval, the atmospheric river just doesn't go away and come back. So that won't happen. So what is the case here is that the thresholding is aggressive enough that it just sometimes forgets about, like drops the label. Whereas on the left-hand side, you don't have that much. It wobbles a bit, but it's technically, you don't have like this sudden vanishing of like objects. So the network actually learns some features which are more continuous in time. Although we haven't fed the temporal component to negative explicitly. So that's quite remarkable. So we want to do this next, so basically also having like a feeding like a sequence of images to do some temporal correlation. That might even improve this result even further, with the human annotated labels in that case. Okay. Deep learning HPC converge. I think you agree on that, right? We talk about that. And you can get exascale performance, even so like TensorFlow is a community developed code. I mean, there's a lot of like vendor effort under the hood going in, but technically you can use it and scale it out very nicely with Horrobot, and then if you go to extreme scales, if you do a little bit of more work. So like the DOE facilities, to say that, so like the supercomputers in the DOE system, they are like very well suited for that, for these kind of problems. And I think more and more HPC systems we're going to buy will have accelerators which can accelerate deep learning tasks and others suitable for these problems. The software enhancements we did can benefit the deep learning community. So like the Horrobot ones, we have a couple of PRs open. We have a couple of like performance bug issues with TensorFlow. So hope they will fix this. And yeah, we think there's exciting times for deep learning in science. So this work was awarded with the ACM Gordon Bell Prize, which is like, some people call it the Pulitzer Prize of HPC. I don't know if I would say that, but the thing is, it usually gets awarded when you have an interesting science problem, you need a massive amount of compute, and you can demonstrate that you could solve the science problem with this massive amount of compute efficiently. Okay? So, and that is 2018, and we got this award for that. Okay, so this is the link to the paper with a bit more information. This is, so Google was interested in that, so they like they like the cool TensorFlow stories, right? So they made a YouTube trailer for the TensorFlow Dev Summit last week? Yeah, last week. You can check it out, it's very cool, it's a 3-minute video, it's very nice. So they flew in even a video producer from the UK for that, so it's quite nice. Okay, yeah. Thank you very much, and are there any questions?